Hello, welcome to a video on section 5.1, part 1, which is about fundamental identities. We'll start with defining an identity. Identity is simply an equation that is always true for any x value. So for example, x plus or equals x. That is an equation because you see an equal sign, but more specifically we're going to call it an identity because if I plug in any value for x in this equation here, it's always going to be true. So x plus or equals x, so if x is 5, the other side will be 5. If x is 10, the other side is 10. Likewise with the other two equations you see below, x times 1 equals x. But, actually I take that back. That right there would not be an identity because this would only be true if x equals 2. So only the first two equations you saw there were identities. So we're now actually going to look at this in terms of trigonometry. We'll start with the reciprocal identities, which you guys should be familiar with. For example, sine theta equals 1 over cosecant theta, and cosecant theta equals 1 over sine theta. Also, cosine theta equals 1 over secant theta, and of course we know secant theta equals 1 over cosine theta. And then tan theta equals 1 over cotangent theta, and cotangent theta equals 1 over tan theta. So those are called reciprocal identities. Those will always be true regardless of what value we plug in for theta. The quotient identities are the following. Tangent theta is sine theta over cosine theta, which makes sense when we think about the unit circle, because remember tangent was y over x on the unit circle, and if you were to draw a triangle, remember we'd have like that'd be y, that'd be x, and that'd be 1. Our sine was y, our cosine was x, so sine over cosine gets us tangent. Cotangent theta will be just a reciprocal, cosine theta over sine theta. And then the Pythagorean identities are the following. Sine squared theta plus cosine squared theta will equal 1. The reason why that's true is unit circle. If you think about it, that was x, that was y, and that was 1. X squared plus y squared equals 1. And since x is cosine and y is sine, that makes this identity true. And another thing to keep in mind as well is that when you say sine square theta, it actually means you got to take sine theta first and then square afterwards. We just put this square symbol right there just to make it look shorter. So that's why it's called the Pythagorean identity, because it's using Pythagorean theorem to derive that identity. And this will be true for any value of theta. If you plug in any number or angle for your theta or x, that's always going to be true. There are two other ones. The other ones will be the following. 1 plus tan squared theta equals secant squared theta. And the other one's going to be cotangent squared theta plus 1 equals cosecant squared theta. Now, you do need to know these. I'm not going to actually give these to you. This one is easy to see because we're just using Pythagorean theorem and we know the unit circle now. So I don't think that's so bad. These two can be derived from the first Pythagorean identity we just talked about. How would you derive those? What you would do is to get this identity, you divide both sides of sine squared theta plus cosine squared theta equals 1 by cosine squared theta. I'll let you think about that, and we can go over that when I see you guys again on Monday. Or over here, you do the same thing, but then you divide both sides by sine squared theta. So if you took this identity and divided both sides of that identity by sine squared theta, that would get us this one here. And of course, if we divided sine squared theta plus cosine squared theta equals 1 by cosine squared theta, we would get that second identity right there. We'll actually kind of work out the nuts and bolts if you want to see why that's true. You can try on your own and actually divide by cosine squared theta to see what actually happens. But that's how you get those. So let's look at some examples here. Tan theta equals 3, cosine theta is greater than 0. So what this implies is that tangent's positive, cosine's positive in the first quadrant. Here is theta. And remember, tan is going to be opposite of adjacent. So that's 3 over 1. That makes that root 10. So our secant theta, which is 1 over cosine, so we know cosine theta is going to be 1 over root 10. Therefore, secant theta will be root 10. We know that the sine theta is 3 over root 10. So therefore, our cosecant theta will be root 10 over 3. Let's try another one. Here cosine is positive, but here tan is negative. So clearly we're going to be in the fourth quadrant. This will be 0.8, that would be 1. If you work it out, you get 0.6. We'll call it negative 0.6 since it's going down. So sine theta is easy. That just gets us negative 0.6. And then tan theta, now we can use our identities. We know it's sine over cosine. Negative 0.6 over 0.8, which gets us negative 0.75. Or you could say negative 3/4. And you could even do opposite adjacent for that triangle as well. Let's look at some simplifying problems. Like this one here. Cotangent is 1 over tangent x. And so if you do that, you just get 1. Or this one here. Cotangent is cosine u over sine u. Those cancel, just get cosine u. This one's interesting. Now if we go back and look at one of the Pythagorean identities, this is actually one of the most crucial ones. This one right here, very, very important. If we think about it, we know that sine squared theta has to equal 1 minus cosine squared theta. That's if we just simply subtract both sides by cosine squared theta. So when we have 1 minus cosine squared theta over sine theta, that will be the same thing as saying sine squared theta over sine theta, which just gets us sine theta. And then up top, if we rearrange some things, sine squared u plus cosine squared u plus tan squared u over secant u. Well, sine squared plus cosine squared is 1. you get 1 plus tan squared u over secant u. And then using our identities from up above, 1 plus tan squared is secant squared, so you can substitute secant squared u over secant u, and that just gets us secant u. So you'll see some practice problems like that as well. Just some strategies to keep in mind when you're simplifying trig expressions. Definitely look to factor. Like in this case, I can factor sine x, is you get this, which would be sine x times 1 or sine x. Try foiling, if that makes sense. Like in this case, I get secant squared x minus 1 or sine squared x. If we use our identities up above, secant squared is 1 plus tan squared. Oops, sorry about that. Yeah, so then if I subtract the 1, I can say tan squared x over sine squared x. Tan squared is sine squared x over cosine squared x. And of course we have the sine squared x in the bottom. Boom, boom. I get 1 over cosine squared x, which is secant squared x. Combining fractions, find LCDs. That would make a lot of sense. If I multiply top and bottom of this by 1 plus sine x, top bottom of this by 1 minus sine x, you have 1 plus sine x plus 1 minus sine x. Boom, boom. Of course, in the bottom we have this. So you end up getting 2 over 1 minus sine squared x. Well, remember, sine squared x plus cosine squared x equals 1. So cosine squared x equals 1 minus sine squared x. So we can substitute and write it as 2 secant squared x. And then lastly, try factoring again if you see the difference of 2 squares. That sometimes can make sense. Because I don't think we have an identity for tan squared x minus 1. Yeah, I mean 1 plus tan squared, but not 1 minus tan squared. So sometimes don't try too hard to find an identity. Sometimes just simple factoring can make all the difference. Okay. So it looks like we're all set. So definitely try the classwork now. There'll be problems similar to what you just saw here. And we're all done. Alright, I'll see you guys on Monday. Goodbye.